Okay, so we'll be getting on with class number 8 for Math 9. We're almost up to the end of this unit. This will be the last concept. The class after this one will just be to prepare you for our final review. So let's get on to this concept. Again, this is the second last class. The last class will be a short one. This is the second class. So we're getting there. There's a light at the end of our tunnel. Identifying types of symmetry on the Cartesian plane. So, first of all, let's review what a Cartesian plane is. It's a fancy word, but it's nothing very complicated. Not even slightly complicated. It's the grid that we're so familiar with the 4 quadrants. That's your Cartesian plane right there. 1, 2, 3, 4. Right, this here is positive. Up top is positive, below is negative. And of course, when you're going backwards horizontally, that's negative. Forwards horizontally is positive. Upwards vertically positive. Downwards vertically negative. There's your Cartesian plane. You can label your numbers if you like. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Negative 1, negative 2, negative 3, and so on. Negative 1, negative 2, negative 3. And here you have your origin, 0, 0 in the middle. There's your little review of a Cartesian plane. Nothing new, right? So let's look at some shapes. Symmetry on a Cartesian plane. You already know what symmetry is by now. So what kind of symmetry do each of these shapes have? Look at the little focus bullet right here. Identify and classify line and rotational symmetry. That's going to be the concepts we're looking at. So what kind of symmetry does this, if we were to take this shape and turn it, what kind of symmetry would it have? This little crab here. How many times would it coincide with itself if we turned it? If we turned it 180 degrees, I think this particular one would have to come all the way around. There's never really a point where you're going to get it coinciding with itself again, like if you were to draw a tracing. This butterfly here, pretty well the same thing. You're not going to have it, you're going to have to come all the way around. There might be this star here, that should work. That should coincide with itself several times. The starfish. The grasshoppers, no, because they'd be upside down, so that wouldn't work. So they have to come all the way around again. This guy, the dragonfly, well, when he comes all the way around here, the head would be down here. So that wouldn't. It'd have to come all the way around again. This guy might. So probably, yeah, I think this guy would maybe coincide a few times, and the starfish. And the others would need to come all the way around. So they wouldn't have rotational symmetry. But 2 of them do. So this is a review of our previous concept. You can stare at this picture as long as you like, but I'm going to move on to today's concept. For this activity here, the investigation activity, they're suggesting a triangle. I'm going to use a square. So we're going to make a square, and we're going to translate the square 2 units right and 2 units down. Then we're going to rotate it 180 degrees about one of the vertices, and we're going to reflect it in a line as well. Rather than a triangle, I'm going with a square because I'm stubborn that way. So we're going to put a square on a Cartesian plane, just like they're suggesting we should put a triangle. So we're going to make a Cartesian plane. and we're going to put a square on it. I'll make this a nice 5 by 5 square. And I can label my vertices. The first one, 2 across, 1 up. That's 2, 1. 2 across and 1, 2, 3, 4, 5, 6 up. 2, 6. 1, 2, 3, 4, 5, 6, 7. 7 and 6. 7 across, 6 up. And finally 7 across and 1 up. So the instructions are to translate it 2 units right and 2 units down. So what you simply do is you take each point and you move it 2 units right and 2 units down. And I'm going to have to extend. To move to the right, I'm going to have to extend this Cartesian plane quite a bit to move to the right. So just take one of your points, take this one, 2 units right, 2 down, there's your first point. Take this one, move it 2 units to the right and 2 units down. Take this one, move it 2 units to the right and 2 units down. Take this one, move 2 units to the right, 2 units down, and make your square. As your first bit of instruction is to simply translate it 2 right and 2 down, and you do simply make a point for a new point for each individual point, and there is your new shape. And this would be an example of a rotation. Could also rotation or a translation. We could have done this instead of a translation. We could have done a rotation, just turned it. Right? But yeah, we call this more of a translation. Let's do a rotation. I'm going to do make a fresh shape every single time. So you got this one, moving up. Of course, you can always pause. That's the advantage of this. You don't need to tell me to slow down or shut up. You can just hit the pause button. It's fantastic. So let's just this time we don't have to make the same square in the same place every single time. Doesn't matter. We're just illustrating a concept here. That's what they suggested, but you know, don't always have to do what they say. So we're going to make a 5 by 5 square, this time on the other side of the thing. And we want to rotate that square 180 degrees according to this point here. They said for the triangle, they said point C, vertex C. I'm going to simply use this point here on this corner to rotate my square. Could I get this one, this one, this one? I'm choosing this one. So I'm going to put my protractor right here, and I want 180 degrees. Here's 90 already. I want to go in a straight line. So that's all the way over here. So I simply rotate this triangle 180 degrees. So that means it'll be over here. Okay? And so I have one of my points. Now all I have to do is, based on this point, make another 5 by 5 triangle. Voila! 180 degree rotation from here to here, or to here. This just happens to be all the way over here because of the size of my protractor. But this here, from here to here, is 180 degrees. From here to here. The point is, you're doing a half circle every single time, right? No matter from which point to which point, it's a half circle rotation, not a full circle, not a 3/4 circle, a half circle which is 180 degrees, half of a protractor. Reflection in a line. Okay. Last introductory concept. Let's make another square. A brand new square, 5 by 5. And this time I'm going to make a 5 by 5 square that's hugging the x-axis, the horizontal axis. And we want to flip it right over, a reflection in a line. Oh. Want to flip it right over the line. So, boom. It's like this. There's your new shape. There's a reflection. Let's say it had been here. Let's say it's just off the line, like this. Then I simply leave a space on the other side of the line as well. Boom. There's my reflection. A reflection has to be identical. Same place, same shape. Then it's a reflection. So reflection's probably the easiest one to do. Then probably a translation. Rotations can be confusing. Like once you get beyond 90, 180, they can confuse you. Don't let them, but they can. Just a bit of a heads up about that. Some definitions. Let's record some definitions and then look at some more examples. So we've done, what are the types of symmetry? Types of symmetry on a Cartesian plane, which is just a grid, a 4-square grid. That's all it is. Types of symmetry on a Cartesian plane. Well, you can have no symmetry. You can have line symmetry, where you reflect over a line. The last example we did. This is line symmetry. Reflect over a line. You can have rotational symmetry. The 180 degree rotation that we did, the half circle, that's rotational symmetry. You can have both line and rotational symmetry in the same shape. Both line, and that's when you do a translation like the very first one we did. Both line and rotational symmetry. You're combining the two. You're not just flipping it over a line, you're also moving it over. And you're not just rotating it, you're also moving it. Rotation, it changes its position, but it's still proportional, and it only changes its position according to a rotation. It doesn't go sideways or up or down, it just rotates. There's a difference. So both line and rotational symmetry, that will combine a rotation and a translation. Line symmetry is a simple flip. Rotation is when you turn, and you can also combine the two. Let's have a look at some more examples. Best one is on 369. I like that one. It does a nice job of illustrating the point. Let's start there. Are these shapes on 369 right here? This one I don't particularly like, so we'll skip it. In fact, their diagram isn't accurate. I don't care to really get into it. If you want to look at it, figure it out yourself. It's not a very good example of a 180 degree rotation. It says we're supposed to be doing a 180 degree rotation around point E. Well, then they go ahead and label point E at 0, 2, right? 0, 2, but that's not what the example says E is supposed to be. The example says E is supposed to be at -1 and 2. So that's an error, and I'm not interested in using this example because of that. You know, won't bother. I'm going to waste our time on that. So here we are, page 369, example number 1. Is each pair of rectangles related by symmetry? So these rectangles here, are they a example of line symmetry or rotational symmetry? Are they or are they not? So take a look. There's the original shape. There's the new shape. This moved down, one down, and then across. Like if we look at point A, it moved down two, and then 1, 2, 3, 4, 5, 6, 7. Oh no, down only one, sorry. 1, 2, 3, 4, 5, 6, 7. 1 down, 7 across. 1 down, 7 across. 1 down. So, is this shape related by rotational symmetry? Let's look at their explanation. There is no line, this is A now, on which a mirror can be placed so that one rectangle is a reflection of the other. So they're not related by line symmetry. So the question is then, are they related by rotational symmetry of 180 degrees? And the answer is yes, they are. Now let's go back and show you so that you understand. Here's my little protractor. If I go to point C, and I rotate, and I get to exactly where this new shape begins. B, I rotate, and again, it takes me to a point on the new shape. So they are related by rotational symmetry, or by a translation, as we showed, 1 down, 7 across. Each shape is 1 down, 7 across. So it could have been translated, it could have been rotated, but they are related by rotational symmetry. This one's easy, I hope. Clearly, this is a reflection. This shape is simply flipped to make this shape. Yes, of course, they are related by symmetry. Let's just check that we're correct about that. Each point on ABCD has a corresponding point on EFGH, and they are both the same distance from the x-axis. They are related by reflection and by rotation, as it says. You could have rotated and you could have also reflected. They both work in this case. Okay. What have we got here? One rectangle basically rotating over the other. Now obviously you should be able to see that if you continue rotating this rectangle, it's going to coincide with itself again. So obviously these angles are related by rotational symmetry. It's only, this is a quarter turn, right? First turn. Turn it again at the half, they'll coincide, and they'll be like this again, then they'll be back up top. So you can clearly see just like that this is clearly rotational symmetry right here. Simple. It's just one shape. You make a tracing of one shape and you turn the shape on top of the other. Simple as that. Okay. Let's go over to page 370. We're going to do these on grid paper now. Alrighty. This example starts at the bottom of page 370. Let's read the question first. Draw the image of rectangle ABCD after each transformation. Write the coordinates of each vertex and its image. Identify and describe the type of symmetry that results. I'm not sure why we're supposed to describe the symmetry when they're already telling us what to do, but whatever. A rotation of 180 degrees about the origin, so that's going to be a rotation. A reflection in the x-axis, that'd be a reflection. The translation is going to be a combination of both, but for some reason we're supposed to describe them even though they're already telling us what to do. But math textbooks, schmath textbooks sometimes. So let's sketch the shape. And then we'll follow their instructions. And then I guess at the end we'll describe what we did. So the first one. So this shape begins here at -1 and it's going to go all the way to +3. Now we're saying a rotation of 180 degrees about the x-axis. Oh, about the origin. So here, origin is always at 0, 0, right there where the two lines meet. So we're going to rotate this shape according to the origin 180 degrees. So here it's a 90. So we're just going to make our mark down here. There's our 180 degree mark right there. And so the origin was the center of our shape. So then the shape, it was right, there was one square behind the origin, and we've landed in the middle of a square here. So we're going to move the beginning of the shape back to the middle of the other square and just make it like this. So it's supposed to cover 4 squares, so now it's already covered 2.5. So 3 whole squares plus 1/2 of each of these squares. There's a 180 degree rotation. That was easy, I hope. See, we started at the origin. So then the point that the origin point was translated over here, and then that becomes the starting point of our new shape. So if this original shape was 1 square behind the origin, then we had to put the new shape starting at approximately 1 square behind the origin. My drawing is not perfect, obviously. I'm as bad as the textbook, but you get the point. Let's make the shape again and follow the next set of instructions. Put the shape exactly where they have it. And they're saying a reflection in the x-axis. So we're simply reflecting it over the horizontal axis. Done. What more do you need? So, oh yeah, we're supposed to say what we did. So, rotation 180 degrees. Reflection x-axis. Like so. And the last bit of instruction, 4 units right, 1 unit down. A translation. Let's build our new shape. Our original shape, I should say. And just take one point and move it. Take your starting, take this point. That's the start of your shape. That's the easiest thing to do. And take it 4 units right. 1, 2, 3, 4. And 1 unit down. And the rest of the points, you don't need to do it this way. Now you've got your original point and you can just make your new shape right here. You could have, every single one of these. 4 right, 1 down. 4 right, 1 down. If you want to waste your time, by all means do so. But once you've got your original point and you know what your shape looks like, then you just make it and you're done. So this is now let's see, this obviously is a rotation. Let's have a look at what kind of rotation it became. And you can see it was 180 degrees. We started, if we take this point where the point that I used to make it, here, it rotated 180 degrees. Boom. So this translation became a 180, basically is a 180 degree rotation. It could also be a reflection if you reflected it over this point. Let's say this was point A, just for an example. You could have said a reflection through point A. Flip it over. You could say that. All right. Page 372. Rotations of a pentagon, which we're going to sketch and do. Let's look at it first. Draw the image of the pentagon. Label the vertices with the letters, I guess, and then follow the instructions. Translation 2 units to the left, translation 2 units to the left, and 3 units down. Alrighty. This will be clear as mud by the time we're finished. So, a Cartesian grid. That's just simply to sound smart. We call it a Cartesian grid. There's probably some Greek meaning behind it. Let's look at where the points are. We're just going to do point R and we'll make everything else around it. Point R is at -2, -5. -2 and down to -5 is point R. Q is 2 above it. Q. S is 2 across from it. T is 1 above S. And then the peak is just 1 right up here. So, okay. Now it's saying move each point 2 units to the left. There's the new T. There's the new Q. There's the new P. There's the new S. There's the new R. Simple. Now, what happened here? We have a reflection. And obviously we have symmetry. We have a reflection. All right, let's make the original shape again. We have a reflection over points T and S. Or if you want to go with the grid description, we have a reflection over -4, -3, and -4, -5. If you want to do it that way. All right, let's make another Cartesian grid. Original shape in the same place, obviously. Where was R again? -2 and 5. I'm going to go with our trusty R again. 5 down, 2 above, 2 across, 2 here, 1 here. Label P, Q, R, S, T. Now, the instructions, 2 to the left and 3 down. There's the new R, 2 left, 3 down. There's the new S, 2 left, 3 down. There's the new T, 2 left, 3 down. There's the new R. No, I've already done that one. There's the new Q. 2 left, 3 down. There's the new P. 2 left, 3 down. Any thoughts on this one? No? Can we reflect this shape? No. You couldn't really just flip it so that it coincides. There's no particular way of doing that. You have to flip it. Just doesn't, because the roof is done in the bottom, so you can't flip it. Can you rotate it so that it coincides? Is it possible to take the original shape and turn it? Will it ever coincide? Like if you look up here, you could take this shape and turn it and eventually it will coincide. This one here, yeah, eventually you get around here, eventually you'll coincide. This shape, you can turn it as much as you like, it'll never fit until it comes back to the, it takes this shape. It's, first of all, this one isn't placed properly, so you could do it. I mean, even if you could, it's only going to coincide. Sorry, you couldn't see this. Start again. This shape isn't really placed so that you could rotate this one anyways, and it would fit into it. And even if it were placed so that you could, like such as the way it is over here, there's no, you can't rotate it. The best you can do is rotate it so that it coincides with itself again at the end. But it never coincides while you are rotating. So it has no rotational. So this here is a reflection. And that's the only way this shape could have symmetry, is with a reflection. It cannot have rotational symmetry. So it's clearly not a reflection. And it does not have any rotational symmetry. This particular shape, there's no point where it would coincide with itself unless you come all the way around, and even then it wouldn't work because it's placed, the translation placed it to where that's not possible. All right, I hope that made sense. On page 373, your homework. Page 373, and that's numbers 3, 6, and then finally page 374, that's numbers 7 and 11. Boom. There we are. Let's look at those exercises. Almost done. The recording's going over half an hour. I like to keep them under, but that's how it goes. Number 3, describe the rotational symmetry and line symmetry of each shape. So, can it reflect? Can it coincide when you turn it? For each one. Are there any that do not, that will only coincide when you've brought them all the way around? I think each of these can reflect a new shape. Not all of them can necessarily rotate and have rotational symmetry. In other words, they won't coincide with themselves until they come all the way around. That's for you to decide and describe. And moving over to number 6, look at the shapes below. Just sit there and look at them. Yep. There's the original shape. The red. Which squares A, B, C, and D are related to the red square by rotational symmetry about the origin? So in other words, turning through here, or by line symmetry, which is a reflection. Now obviously, you should see that this is a reflection through this line, B. C is a reflection over the x-axis, and the other two I'm going to guess are some form of a rotation, but maybe they aren't. Check them. They seem to be well enough lined up though, so they probably will be. But anyways, yeah, this shouldn't be a hard question. They're either rotational symmetry or aligned symmetry, or maybe neither, maybe. 7-11. For each diagram, determine whether the two polygons are related by line symmetry, by rotational symmetry about the origin, or both. So this is the same as what we just did in number 6. Find out how each shape is related to each other. Is it line symmetry? Pretty clear that we have a reflection happening here, so we have line symmetry. Do we have rotational symmetry? Yeah, this one's obvious. A straight line across, that's 180 degrees. Hint, hint, hint. We've got rotational symmetry and line symmetry for 7a. That one's already done, so just identify what's going on in each one. Is it rotational? Is it line? Is it both? I don't think any of them are neither. They both have at least one, and some have two. 11. You get to draw. Copy each shape on grid paper. Draw the image after the rotation given and label, just the way we did in a bunch of examples. So we draw the shape, and then we move it 6 units up. Then we draw this one, and we move it 6 units to the right. That's easy enough, I hope. It ought to be. Okay? So again, page 373, 3 and 6. Page 374, 7 and 11. Just one final thing for this lesson. And that's just a reminder. This was our last concept. The final review is coming up on Friday. So you'll get this recording on Wednesday morning, and then you'll get a brief recording for the final review on Friday morning. It'll be very short, to the point. It won't go on long. We'll just go over which questions you're doing for the review and talk a little bit about each question. And that will wrap up this unit. And we probably will go a few days into next week before we start on the next unit, just to give everybody a chance to wrap up this one. Might be like, maybe we'll go with, for next, we'll talk about that more on Friday. We'll see how things are at. Okay, that's all for today. Adios, au revoir.